on this computer. Okay, so hi everyone. So this meeting is recorded and will be uploaded to YouTube. The first item on our agenda is dynamic resource allocation. So this is a KIP that Patrick is proposing. So go ahead, Patrick.
Okay. How much time do I have? Do you have other people? I haven't checked the agenda. So
so there's only you, and then there's James. James, how much time do you need for the from the release team?
Like a couple of minutes. It's really just an intro and saying hello.
Yeah, I certainly don't intend to occupy an entire hour. So let's just go through the slides.
Okay, so it's just half an hour, by the way. The meeting.
Oh, it's a half an hour. Well, I could still manage. So let's dive right in. Dynamic resource allocation is something that is coming out of observations in the SIG node that current device interface and how people request devices is too limited. I've done a presentation, or this whole CAP has been discussed already in SIG node in the middle of December. There has been other discussions going on earlier around it, and the conclusion, at least in SIG node, was that these gaps really should be addressed. So we should rethink the entire API that we expose to users, how they manage devices, or in general resources, for things that are more complicated than just RAM and CPU. And that's how this CAP came about. There is another related effort, the container device interface effort, that is about the low-level part, extending what container runtime support. And this CAP here is about the Kubernetes side of that, making container device interface usable in Kubernetes. The proposal, roughly speaking, is to take ideas from the volume API, and that's where I come in, because I've done most of my work so far in Kubernetes in SIG storage around volume support, CSI support. And we are taking some of the same ideas. You will see familiar names if you know storage in this later slide, and try to apply that way of requesting something. In SIG storage, it's a volume. In our case, it's some more abstract resource through a different API that is more flexible than what is available in Kubernetes at the moment. Another observation is that because these resources could be a specific hardware device, but it could also be something else, and we just don't know. We want to come up with a solution that is generic enough that vendors or Kubernetes don't need further changes once we are done with the initial implementation. And that's why the API has custom parameters in some of the objects that are entirely dependent on the third-party cluster add-on and don't have any meaning to Kubernetes components. They just get passed around, but they need to be in the API because otherwise the user wouldn't be able to specify them. Along the same line, the idea is that in Kubernetes, we do some support for this generic API, and then vendors add third-party add-ons in an easy way without having to modify Kubernetes, for example. Because some of these hardware vendors and customers, they might not be experienced with Kubernetes development. So there needs to be a fairly simple way of deploying something that's probably in the same order of complexity as deploying a CSI driver. Now that's the summary. Some of the motivation. This is where we spent more time talking about these slides in SIG node meeting, because we really wanted to understand the use cases. For SIG scheduling, I can go through those, but I think it's perhaps a bit less interesting because it's very specific to what's done with devices.
I think it would be useful if you can actually mention a specific example, so it's easier for us to relate.
So one example that keeps coming up is sharing a GPU. This is supported by the hardware. You can basically tear down, or you can split up the GPU into, say, certain segments, or I don't know what they call it, slices, and those are basically reserved for certain applications exclusively. This is kind of supported by making the extended resources count, say, memory, but it's not very flexible. And there are other things like adding additional instructions for the GPU on how to make the GPU available that just can't be specified in the current API.
Are you talking about MEG?
MIG is one example where NVIDIA is currently investigating what they can do with this cap that they can't do at the moment. Yeah, that would be one specific example. Another thing that may be relevant is for FPGAs, for example. They can be kind of hard to program, and setting up an FPGA to do some specific tasks may be expensive, and it might make sense to do that setup once and then reuse that already initialized accelerator multiple times in different workloads. And that depends on an API that actually allows specifying how to program an API. That's the custom parameters again. And an API that allows allocating this hardware with a certain configuration and using it in multiple pods, one after the other, or perhaps even in parallel if that's supported by the hardware. That's again a different API that we are talking about. And finally, at the low-level kubelet level, but which is again more relevant for SIG node, the observation currently is that runtimes have to be modified to support, say, an NVIDIA GPU. And we want to get to a point where that is no longer necessary, that with CDI, we have a vendor-independent standard of how to reconfigure a runtime and add devices without having to modify the runtimes for every single new hardware device. In terms of implementation, the generic part will be in Kubernetes, and there are things, it basically needs to touch quite a few places. Obviously, the API server, we want to introduce a new API, and because it is used by in-tree components, it will be a new API group. It will be a completely new one, so it doesn't interfere with anything that exists right now, but it needs to be defined by the API server because a custom resource definition basically has deployment issues. We can't be sure that it's actually in the cluster, and therefore a controller manager can't depend on it really. All of these problems get avoided if we just make it an in-tree or internal or official Kubernetes API. There are
here, like you're talking about new resources, new object APIs. Can you highlight that? Like it's not clear from this slide.
Yeah. So resource claim is the key one. It corresponds to a persistent volume claim for volumes. And that's the key object that users interact with if they want to allocate something. And that resource claim is a standalone object created by a user with a status, a specification of what it's supposed to allocate, and the status that explains what has been done already for that claim.
So my question about resource claim is that, is it a generic claim to abstract like all kinds of resources or devices?
Yeah. No, there's no attempt to abstract away from the underlying API provided by the third-party cluster add-on. So there was a previous attempt in the past to define an abstract resource class, basically saying, I want a GPU. This easily becomes then problematic because you have an abstraction, you have something new that doesn't fit into the abstraction, and then you end up having to modify the abstraction again to support new use cases. So this proposal here has a resource claim, but embedded inside it is, I forgot what the API object is, but it's basically a placeholder for arbitrary parameters. Could be lists, could be a map, could be just a string.
How does this get validated?
The third-party cluster add-on can do an admission controller, and because it sees the resource claim before the object gets created, it can do validation. Otherwise, if a third-party cluster add-on developer doesn't want to do that, the resource claim gets created, and the cluster add-on at some point will be called for this resource claim, and then it can throw an error, and the pod that used, or the resource claim basically then would be an invalid state and it won't make any progress because it's invalid. That's of course not as user-friendly, but it would be simpler for the third-party add-on developer. So both is possible.
It sounds like we are going to introduce the Golang generics.
It is a kind of a generic thing in the API. There is an object that can hold arbitrary JSON essentially, and that then gets converted into a Go object, and internally you can iterate over fields and make sure that it contains what it's supposed to contain. But in the API, it's just a blob essentially. So
if I were to summarize, like for example, who's creating the resource claim? Is it the resource claim controller? So can you describe the workflow? Like the user creates what, and then we end up with what?
Yeah. Let me see what I have it in the later slides, but I can also answer that. It's we have two cases. One is where the user directly creates a resource claim and it's independent of a pod. That's the use case where this resource gets allocated once and then may be referenced by multiple pods at a later time. So that would be the user creating the resource claim. What we see here is the more complex scenario where a pod gets created by the user, and the pod contains an extension saying, please create a resource claim for me. That's the inline resource allocation or resource claim thing, where the resource is clearly meant to be for the pod and no other pod ever gets access to it. And the life cycle of that resource allocation is the same as the pod. That mirrors, if this is basically how the current resources get allocated. You basically specify them in the pod. You don't need to do anything special, and Kubernetes takes care of reserving resources. That is the other use case that we are supporting, and we do it the same way as in storage. In storage, there is a feature that I introduced called generic ephemeral inline volumes. It was based on the observation that a lot of code exists for dealing with persistent volume claims, but the user still needs to manually create those. And that if we allow an inline specification of a volume claim inside a pod spec and then have some code here it's called resource claim controller, but there is something similar for volumes that just takes those pod definitions and creates the resource claim, then we can use existing storage drivers without any special cases in the plugin or in the CSI driver, or here in this case in the cluster add-on. They just work with these standalone objects, and both use cases then get dealt with in the same way by manipulating resource claim objects. So the interesting part for today's discussion is how the scheduler actually interacts with this whole thing. The envisioned solution is that we will have another scheduler plugin which gets provided, gets implemented in Kubernetes, gets linked into kubescheduler, and it knows about the extended pod definition. It knows about resource claims, so there will be a watch on Informer for resource claim objects that this feeds into this resource plugin. And then if there is a pod that uses or has an embedded resource claim or references a resource claim by name, then this plugin does the checks whether this resource is already allocated and makes sure that it gets allocated if the binding or the allocation mode is such that it waits for the pod. But this is coming later. I just wanted to say that this is where we have the scheduler specific functionality. And then in kubelet we have the same thing. We have a pod getting scheduled or which got scheduled onto a node which uses such resources. Then a local node resource plugin gets called to actually make the resource available and add it to the container when the pod needs to run. Let me skip over that really quickly so that we can get to the scheduler part, because that's really where I want your feedback.
So this is a pod level, not container level.
Yeah, the resource gets allocated for the pod, and then containers inside the pod can use it.
Okay.
Yeah, it references basically, it's the same concept as in storage. In storage, you specify volumes, and inside the container, you specify volume mounts that basically say, I want this container to have this volume mounted. And here we are using the same thing. There's another indirection with resource classes. That's for storing privileged parameters that only an admin can create. So the resource class basically gets created when an admin deploys a third-party add-on and configures it for the cluster. The resource claim is what the user creates, and the resource claim template is the corresponding thing embedded in the pod spec.
So one question about the provision of this kind of dynamic resource. Let's say we have defined a resource XYZ. So who will provision the concrete resource XYZ? Is the
it's
Kubernetes?
No, it's a third-party add-on. So the third-party add-on must have some resource controller which runs in the control plane. So one instance per cluster essentially. And that's where this controller basically interacts with a resource claim object. This is another idea here that the CAP, I don't know, introduces, that all communication happens through updates of resource claim. There's no need to set up direct communication between these components, because my observation with scheduler webhooks has been that securing those is tricky, depends on custom APIs, say in OpenShift to create certificates, or becomes harder for users to set up correctly. So this proposal here is that all of these objects are normal, all of these components are normal Kube API server clients, and they just talk to the API server if they want to change something. It's like a shared whiteboard where we describe the current state and what needs to happen.
So there are two cases for provisioning, right? Like there is one where the resource is not local to the node. And and the other case is where it is part of the node, and I can map that to network attached storage and local SSDs.
The third-party add-on basically knows whether it's network attached or whether it's local, and that's hidden to Kubernetes, but there is information in the resource claim status to tell the scheduler where the allocated resource is available.
Yeah.
Whether it's on multiple nodes or just one particular node. And the allocation with the scheduling, I'm coming to that. There needs to be some additional feedback loop between those different components to figure out on which node a pod actually can run.
Yeah, one idea can fit this scenario is like some cloud provider has the floating IP or dynamic IP, and they want to assign the floating IP to the specific pod. And this kind of floating IP can be described as this kind of dynamic resource, and they have their third-party controller to attach the floating IP to the specific node, so that the specific pod can use, sort of like that.
We actually had a question from Tim from I forgot the full name, but whether this API could be used for something that is not a device. And I certainly think that the resource claim object is generic enough to also support such use cases. It wasn't the primary purpose, but it could be used for that. And what that really means for the pod then is entirely up to the third-party add-on to make it happen.
So, I mean, like at the end of the day, what you're describing here as that external controller is like a provisioner, and cluster autoscaler is a provisioner, but for nodes, right? So you can consider the node itself as well. CPU and memory is part of that thing if you want to make it even more generic. And I'm just trying to think, because we've been thinking as well as something similar, like how do we communicate to cluster autoscaler that I want to provision some capacity before we actually create the pods, or like when I create the pod. Like I don't want cluster autoscaler to, right now, if you know, like cluster autoscaler basically reacts on unscheduled pods, but we are thinking about having an explicit API, and I'm just trying to draw parallels, and maybe somehow, somewhere we can make that happen under the same. And actually, we were discussing the exact same name, resource claim, to be frank, like internally. So I was just thinking maybe we can do something with it and extend it to support CPU and memory, basically.
Yeah, but perhaps my concern is that if we replace the existing resource allocation with this thing here, it will be too slow. I certainly see a value in how the kube scheduler currently works, where it basically counts things and allocates itself on behalf of a pod. That can be done quickly. This protocol that I'm proposing is something that I expect to be a lot slower, because it has to be so generic and has to call out and has to work with third-party plugins. So I need to speed up, otherwise we just have 5 minutes. The scheduler plugin is where I see the logic being implemented inside Kube Scheduler and being implemented once. Compared to alternative solutions like webhooks or custom built schedulers, the advantage really is ease of deployment. And perhaps that a pod that uses hardware from different vendors can still be scheduled. If you have one scheduler per hardware device, you basically can't combine those different hardwares in a single pod, because which scheduler of which vendor would be responsible for it. Anyway, this is from the cap. If you want to look at, or if you do have time, please definitely go to the cap, and you will find this diagram. It continues on the next slide, explaining how immediate allocation, that's where basically the resource claim gets allocated without interacting with a pod. Perhaps it's so important that we first allocate the resource, and then when it's allocated, the pod simply has to run where the resource is available. The other case is the more complex one, where we have an inline resource, a pod uses that, and we need to allocate the resource on a node or for a node where the pod actually can run. So it's an interdependency between available CPU, available RAM, and availability of these third-party resources that drives the pod scheduling. The current thinking here is that the scheduler plugin does the usual calls into this resource plugin, filters nodes, and then asks the plugin whether that node selection is okay. The generic part in Kube Scheduler doesn't know. It basically has to reach out to the third-party add-on, and it does that by updating the resource claim, specifying, yeah, we are currently investigating in Kube Scheduler that these nodes might be useful for, or might be suitable for the resource, and then the resource controller checks whether that set of nodes actually fits the resource. If it does, it responds back saying, yeah, I checked that. You can go ahead with pod scheduling for this subset of the nodes. And then the next time the scheduler looks at this pod, probably triggered by an update of the resource claim, it will then see that there is indeed a node that is a candidate for the pod. That calls into the resource plugin again with a request to proceed with that node. And at that point, we can do the same thing as for volumes with the selected node annotation. We just update the resource claim saying, yeah, we have selected a node. We now need to get the resource allocated for that node. And then when the third-party add-on sees that, it can do the actual allocation. The whole point here is that this allocation ideally should be like a reservation. It should make sure that the resources are available when the pod got scheduled. That then once it's scheduled, that nothing goes wrong and the pod actually can start to run. This is not the case with several other situations right now, where Kube Scheduler doesn't have the full information about what is possible on a node, and then kubelet finds that it's supposed to run a pod but can't because something isn't aligned right, and the pod basically gets stuck on a node. There is a feedback loop here, where if allocation fails, the third-party add-on can update the status of a resource claim, and Kube Scheduler will see that and try again with some other nodes, until eventually there will be something there where the pod can be scheduled to. I need to continue on the next slide. This is a very tall diagram or flow diagram.
One thing to be aware of is cluster autoscaler. How does this work with cluster autoscaler?
It's the same problem as with volumes. It's fine for network attached resources. The third-party add-on basically could select the suitable nodes with labels, and then if the fictional node matches those labels, the autoscaler knows that it can create something. But yeah, this needs further investigations, I suppose. And like with volumes, we need to investigate that. But it's not necessarily a problem for everyone. So I see value in this proposal here also in clusters that don't use autoscaler. So I wouldn't necessarily block development of this feature just because we haven't figured out how to support autoscaler yet. This, in my opinion, that can come later, and we will certainly have a long alpha period with this, where we figure out how to make it work without autoscaler, and then before we can go to beta or GA, we can make it a milestone that autoscaler also needs to work. There are some other things that happen once the resource is allocated. We have a concept of using a resource by one or more pods, and this can be a limitation imposed by the third-party add-on, basically specified in the status, and then the Kubernetes part knows about this limitation, makes sure that only that this limitation is honored, and it always knows which pod is assigned or is allowed to use a resource. Only those pods really can run and get scheduled, and in the end, we tear down the whole thing. The pod gets deleted. On the kubelet side, we unstage or unprepare the resource, and that makes it available again for reuse by other pods. Or if it's an inline resource, it will be automatically get a deletion timestamp, and that is the signal to the resource controller that it can deallocate the resource and free everything, and eventually the resource claim object itself will get deleted and removed. So this is how we envision this to work. This is certainly a lot of work. We would like to get started, and that means getting the cap into an implementable state merged. And we would like to get started for 124. Whether it's realistic to put everything in alpha quality in Kubernetes in 124 is a bit risky. I can see a plan B where we just define the core API, but don't put in the scheduler changes, the pod spec changes, and delay those, say, until 125. But right now, I'd still would like to shoot for 124 and just have that as a fallback plan, where if it turns out that we get the development not done in time. So the role of SIG scheduling obviously will be with the scheduler plugin part, as a reviewer, as a prover, and in the cap, I'm proposing to make SIG scheduling a participating SIG. And my call today, or my question today, is basically if that is if you're comfortable with that and something that you can support. We don't need to answer that today.
No, I mean, I guess that's the first question. So, yeah. I mean, adding it as a participating SIG, that's for sure. Like, if it gets accepted, the SIG needs to be involved in this, because it does make you're adding a new plugin with a new dependency on a new resource type, etc. So we need to be aware of where that cap is going, basically, and how it shapes up.
Fully agree. Yeah.
So I'm happy to review. I start reviewing that cap, but I don't know if, as you mentioned, like what would be the scope for 124. So that I think we can determine now.
Yeah. So the cap also isn't quite complete yet. It was mostly the summary, high-level design is there, but depending on how we're proceeding, we may have to put more details into the section about, say, how the scheduler plugin works. so I can imagine that we will need to put more effort into, or say also the PRR, production readiness review thing is pending. It needs to be added. But if I get the feedback from you also, like I did with SIG Node, that this seems worthwhile, then yeah, let's move forward with a cap. That would be my call to action, basically.
My additional advice would be that even if autoscaling is not considered for alpha, you should still engage early with them so that a possible future solution can be envisioned from now.
Yeah, okay.
I have a question. Yeah, because the pod can preempt other pods with the priority. Does the resource claim can satisfy this?
I'm not sure I fully captured the question. Can you rephrase or repeat the question?
Yeah. Because the pod can preempt the other pods based the pod priority. Yeah. Does this support it?
This doesn't. I think that's orthogonal to this proposal. The resource well, it depends. If a resource allocation is what prevents other pods from running, then yeah, we might want to force a pod to stop, to free up its allocation and allow some other pod to run. This is not this is not currently part of this proposal. It's not covered.
I suggest if there are further questions, please take a look at the KIP. Thank you so much for bringing this up, for our attention. In the interest of time, I'm just going to give James a couple minutes from the release team.
Sure. Hello. I realize we've run over the meeting slightly, so I'll be very brief. My name is James Lavrak. I'm the release lead for the Kubernetes 124 release team. I just wanted to drop in to kind of give a reminder of dates. The production readiness review soft freeze is in week 3 on January the 27th. And a week after that, on the 3rd or 4th of February, depending on your time zone, is the enhancements freeze deadline. I'll put a link in a link in the minutes with the full deadlines and a link to the full schedule. I just wanted to ask if there's anything that I could do to help you, any questions I can answer about the release or about 124.
Any questions? Sounds good. Like if you can post like your Slack channel, basically where people can ask any questions.
Sure.
I'll put it. I get that's one reference.
I'll put it in the minutes now. Cool. Thank you.
And one last thing from Aldo.
Yes, so we have to do an annual report every year, and that's coming up soon, but we don't really have any updates today. Just expect a pull request in the next month, and you'll get a chance to review and add comments if you have any concerns. That's it.
All right. Thank you, everybody, and see you in 2 weeks.
Thank you.